Hello, viewers. In today's session, we are going to discuss an important and conceptual problem from domain of functions, right? And in this class, we'll solve this problem in which we have to find the domain of this function f of x involving the inverse trigonometric functions, right? So here we have f of x is equal to tan inverse square root of x divided by sine inverse x minus 1, right? So here we'll see how we can find out the domain of functions by using the concept of intersection of domains, right? So let us start. So here we have the quotient of two functions, right? Tan inverse square root of x and sine inverse x minus 1. So let us first see the domain of tan inverse square root of x. So here we have tan inverse of square root of x, right? Now see, from inverse trigonometric functions, we know that the domain of tan inverse theta is the set of all real numbers. That is, theta belongs to the set of real numbers. So whenever we have tan inverse theta, then theta takes all the real numbers. Now here we have for theta we have square root of x, right? And since here we have the square root of x, so the this quantity x has to be greater than 0, right? Because x cannot be negative here, because when we have a negative quantity inside the square root sign, then we have a complex number. So here the domain of tan inverse square root of x is x greater than 0 or equal to 0, right? So here x can take all the positive values or the positive real numbers, including x is equal to 0. So the domain of tan inverse square root of x is given by x greater than or equal to 0, which can also be written as x belonging to the set that is 0 to infinity, right? Okay, now let us come to sine inverse x minus 1. Now let us consider the function that is sine inverse theta. Now, when we have sine inverse theta, then this theta must belong to the interval that is minus 1 to 1. That is, theta must be greater than or equal to minus 1, but it is less than or equal to 1. So here for theta we have x minus 1. So let us substitute theta is equal to x minus 1 in this inequality. So we have minus 1, and here we have x minus 1, and here we have 1. So now solving this inequality by adding plus 1 throughout this inequality. So we have plus 1 minus 1, here we have plus 1 plus x minus 1, and here we have plus 1 plus 1, right? So here 1 minus 1 is 0, and here we have 1 and 1 get cancelled, so we have x, and here we have 1 plus 1, 2, right? So we have this inequality, right? And here there is one important thing to note. See, sine inverse x minus 1, it appears in the denominator. And whenever x is equal to 1 or x minus 1 is equal to 0, then we have sine inverse 0 is equal to 0, and we have a 0 in the denominator. And in that case, the function f of x is not defined, right? So apart from this inequality, this sine inverse x minus 1 should not be equal to 0, right? So for this, x should not be equal to 1. So incorporating these two, the domain of sine inverse x minus 1, which appears in the denominator of this function f of x, we have x greater than or equal to 0 but less than or equal to 2, including x is not equal to 1. So now let us call the domain of tan inverse square root of x as d1, and the domain of sine inverse x minus 1, which is given by these two expressions, let us call it d2. So the overall domain of the function f of x is given by, say, d is the domain of f of x. So D is given by the common region between D1 and D2. So we have the intersection of D1 and D2. So to identify the common domain, we have to take help of the real number line. So let us draw the real number line like this. So here we have minus infinity, here we have plus infinity, and let us take here the point 0, and then we have 1, here we have 1, and then let us take here the point 2. So now the domain D1 is given by x greater than or equal to 0, right? So we have this region, that is x greater than or equal to 0 is given by this region. So here this 0 is included. So here we make it dark, and then we have x greater than or equal to 0 but less than or equal to 2, right? So we have like this, and from 0 to 2, and here we have 1, right? And 1 is not included, so we'll make a circle here. So this circle indicates that this x is equal to 1 is not included, right? And here both 0 and 2 are included. So now the domain D is given by D1 intersection D2. So D1 is x greater than or equal to 0. It means D1 is given by this interval, that is 0 to infinity. So here 0 is included, right? And then we have the intersection, and then we have D2. So D2 is from 0 to 2. So first we'll write here 0 to 1. So 0 is included but 1 is not included, so here it is open, right? And then we have union, and then here we have 1 to 2, right? 1 to 2, and 2 is included, so here we have a closed interval, right? So D1 intersection D2 is given by this notation. So now the common region between these two domains, this is D1 and this is D2. So here the common domain is this region, right? From here to here. So from 0 to 2, we have the domain of f of x, excluding this x is equal to 1, right? So the intersection of these two intervals is now given by this one, that is 0 to 1, and here 1 is not included, and then we have the union, and here we have 1 to 2, and 2 is closed. So the domain of this function f of x is given by 0 to 1, from 0 to 1. 1 is not included, 0 to 1, 0 is included, and then from 1 to 2. From 1 to 2, 1 is not included, and here 2 is included. So the domain of f of x is given by the union of these two intervals. So we can also express this notation like this. We can take the entire interval from 0 to 2, that is 0 to 2, and then we can exclude 1 from this interval, right? So we can also write here 1 in the curly brackets.